Hello and welcome to today's video. In this video, we're going to introduce a notion of norms and metrics in vector spaces. So far, we have discussed vector spaces without really taking any measurements in those spaces. We have discussed vectors, bases, linear independence. We have not discussed things like the length of a vector, or the distance between 2 points in a vector space, or the angle between vectors, lines, planes. This is going to change now. In this first video, we're going to introduce notions to measure lengths and distances in vector spaces, and later we are going to extend that to be able to talk about orthogonality and angles between vectors. So this first section is called norm and metric in vector spaces. And again, the idea or the goal of this and the next few sections is we want to be able to define a length and a distance between vectors. So define a notion of length and of distance in vector spaces. We'll start with the idea of assigning a length to a vector, and that length is usually called a norm in mathematics, at least in connection with vector spaces. We'll start with a more or less abstract definition, and then introduce a specific length method that we'll mostly be using in R to the n. However, a thing like a norm, a length of a vector, that can be introduced in many other vector spaces as well. And we will make use of that later on when we're talking about function spaces, for example. So we'll define that in a more general way first. The question that we ask here is, what are the important properties that we want of something that we could call a length of a vector, of an element? Now this is collected in the following definition. So let's start with a vector space. Let V be a vector space. And we look at a function that assigns a real number to each element of that vector space. We call that function n for now. And that's a function with domain V and codomain R. And we call that function a norm on the vector space V if it has the following properties. Now, what properties do we want a meaningful length measure to have? The first is, of course, the length of anything should never be negative. So we only want non-negative numbers. And furthermore, the length of the zero vector should be zero, but only of that one. So any vector that's not the zero vector should have a strictly positive length. So that's the first property we want. So n of x is greater or equal to 0 for all x in V, and n of x is equal to 0 if and only if x is the zero vector. The second property, if we scale a vector, then of course we want the length of that vector to scale with the same factor. So if we double a vector, we want the length to double. If we triple it, we want the length to triple, and so on. So more generally, if we're looking at the vector lambda x for a scalar lambda, then we want the norm of that vector, n of lambda x, we want that to be the same as lambda times n of x. We'll have to take the absolute value of lambda here instead of just lambda, because, for example, if you multiply a vector by -2, then still the length changes by a factor of 2. The vector is also flipped, but that doesn't influence the length. So that's why we have to take the absolute value here in that place. And we want that to be true for all x in V and all lambda in R. And finally, a property that is a little more abstract. If we're looking at the sum of two vectors, then what is the length of those, and how does it compare to the length of the single vectors? Let's have a look at a quick sketch first. So let's say we have a vector x, this one here. We add to that a vector y, this one. So the sum of those two vectors is then this vector here. So that's x plus y. Now, how are the lengths of those related? Well, best case, x and y point in the same direction, then x plus y has exactly the same length as x and y together. In general, however, we'll have a scenario like this. They don't point in the same direction. And so that means the direct connection, the x plus y, is usually shorter than taking x and then y. And that's what is expressed in that third property, which just says, well, the norm of x plus y is at most as big as the norm of x plus that of y. And that is true for all x, y in V. And this property, by the way, is called the triangle inequality. The reasons for this name should be obvious once you look at this picture here. So basically that's all that we want. If a function n has these properties, then we can use it as a length measure on a vector space. And there is, of course, a length measure that we usually make use of in R to the n, so we introduce that. But before that, a quick notation. We usually not use the name n or something like that for a length measure, a norm. We'll instead denote it by a special mathematical symbol. So let's introduce that as well. A norm is usually denoted by, the notation is we have a vector x. We want the norm of that vector x. We'll usually write this as x and then these norm symbols around it. So that is the notation for the norm of a vector x. You'll sometimes also see something like the absolute value of a vector x. I try to avoid that, just to make clear that we're talking about a vector here. The absolute value is usually reserved for real numbers and complex numbers that we'll talk about later on. But for a vector, I usually use the double bars for the norm symbol. Okay, and also a vector space that is equipped with a norm is referred to as a normed vector space. So if I'm talking about a normed vector space, I just mean a vector space with any norm. So a vector space V together with a norm that will often be wrote in this way here. So that's the norm function. And this dot here symbolizes where the argument goes, so to say. And that is usually referred to as a normed space. And now finally, for the r to the n, there is one especially prominent norm that we'll very often use, and that is the so-called Euclidean norm. For the vector space r to the n, the following defines a norm. So if we take a vector x1 to xn and then define its norm to be the square root of x1 squared plus x2 squared and so on up to xn squared, that is a norm on r to the n. And this is the so-called Euclidean norm. We usually use this norm here, so whenever we're working with r to the n and I just write norm, then I usually mean the Euclidean norm. So in r to the n, we will usually write this norm symbol for the Euclidean norm. Sometimes we will also use the symbol norm with an index 2. So the Euclidean norm is also referred to as a 2 norm sometimes. Okay, so that's what a norm can be. Let's have a look at different norms as well, as a quick example. So we've seen the Euclidean norm already, but of course there are other ways of measuring the length of a vector, and those sometimes make a lot of sense. For example, let's have a look at the Manhattan norm. Or sometimes this is also called one norm. That's also a norm defined on r to the n. And the definition is the one norm of x, denoted by the subscript 1, is just defined to be the sum of the absolute values of the components of that vector x. So absolute value of x1 plus absolute value of x2 and so on. Okay, so if you have a look at that and compare that to the Euclidean norm, for example, let's say we have 0 here. Then let's say we have a vector x up there. So this is x. Then the Euclidean norm of x is the distance as the crow flies from 0 to that point here. So the Euclidean norm is the length of this distance here, this line here. That's the Euclidean norm or 2 norm. The 1 norm, on the other hand, is the sum of the absolute values of the entries of x. So the x1 entry is this distance here. The x2 entry is this distance here. Right? So this is x1, this is x2, absolute value. So the total length of those two, x1 plus x2, that is the one norm of x. And you should now also be able to see why this is called Manhattan norm. So the idea is basically that you can't fly like a crowd. You have to use the streets because you're not able to fly. And if the streets are laid out as they are in Manhattan, in a grid form, grid layout, then of course you usually walk like this first, and then at some point you take a turn and walk like this. And of course it doesn't really matter whether you actually take those two streets or whether you instead walk like this here. You can also do this. The distance is the same, right? So basically the Manhattan norm, the Manhattan length of a vector, is the distance you have to walk from your current point to your current point plus that vector if you have to walk through the streets of Manhattan instead of just being able to fly to that point. So as a very quick example with numbers, let's have a look at, say, the vector 1, 3. We can compute the norm of 1, 3, the one norm of 1, 3. That would simply be 1 plus 3. So the one norm is 4 here. In contrast to that, the Euclidean norm of that vector is the square root of 1 squared plus 3 squared. So 1 squared is 1, 3 squared is 9, so that's the square root of 10. Okay, so that's an example for a norm, and another norm that is frequently used is the so-called maximum norm. It's also a norm on Rn. And that is defined as the maximum of the absolute values of the entries of the vector x. So you just take all absolute values, you select the maximum of that, that is your maximum norm, right? So if we copy this little example here, and add the maximum norm. Now we just have to compare which of these is longer, and I would say x2 is a little longer here, barely, but yeah. So this distance here, this would then be the maximum norm. As the absolute value of x2 is larger than that of x1. Okay, and in our example here, 1, 3, if we take the maximum norm of 1, 3, that's the maximum of the absolute values of 1 and 3. And of course, the maximum here is 3. Okay, so this is the maximum norm. Basically, that's the maximum distance of the two that you have to walk. Again, that may make sense, for example, if you're trying to compute an approximation to some given vector, and we'll do that later on, we'll do these approximations later, then basically, if you measure the distance between those two in Euclidean norm, you average out over the distances of the individual entries. So maybe there's a very large difference in one entry, but very small differences in all the others, and you're fine with that. However, if you want to limit the maximum distance, the actual maximum distance, then the maximum norm might be a better choice, because that only measures this maximum distance here. Meaning that you get a smaller value if you can decrease that maximum distance, and the others below that don't really matter. So that's an example for a different norm, again defined in R to the n. Now, I've mentioned it already. Of course, we can also use the notion of length of vectors to measure distances, and let's do just that. So the next definition is on distances. And again, we'll first do a general definition for that. So we'll start with a vector space. And we have a function that we call d for distance, function d. A distance, of course, takes 2 points. So you measure the distance from one point to some other point. You need 2 points as input, so v times v. And it gives you a real number. And such a function will be called a distance measure or a metric. So a metric on v, if it has the following properties. And this is pretty similar to the ones that we had for the norm. The first, again, is a distance should always be a non-negative number. So d of xy is always non-negative for all xy in v. And we want the distance to be 0 exactly if those 2 points coincide. So 2 different points should always have a positive distance. So distance of x and y is 0 if and only if x equals y. The second, something we didn't need for the norm, the distance should not depend on the order of the points, right? The distance from x to y is the same as the distance from y to x. There shouldn't be an asymmetry here. So we want any distance function to have this property, this symmetry property, d of xy equals d of yx for all xy. And finally, again, we'll need a triangle inequality. And the idea here is if we have 3 points, x, y, and a third point, z, then we want the direct distance from x to y be the shortest possible distance. So in other words, if we take a detour, if we go to z first and then to y, so this whole thing is d of x z plus d of zy, that should be longer, right? Or at least as long as the orange direct distance. So that's something that we want of a distance function. The direct distance d of x, y is less so equal to the distance that we get if we take the detour over z. And again, for all x, y, z in v. And again, this is called the triangle inequality for distances. Now, of course, one easy way to get such a distance function is to just use a norm. If we have a norm already, we can measure lengths. And of course, if we have 2 vectors, right? Let's say we have x here, we have y here. There's the origin is somewhere here. Then, of course, we can measure the lengths of x and of y. And more importantly, we can take the difference. So the difference of x and y is this vector here, or pointing the other way for the length, that doesn't really matter. So whether we take x minus y or y minus x, okay? So in this case, it's y minus x. And of course, to measure the distance from x to y, we could just compute the length of this blue vector y minus x here. So this length here is the distance from x to y. And that means if we have a norm on a vector space, then we also have a metric. So if a norm is defined, then d of xy defined as the norm of x minus y or y minus x, the order does not make a difference, that defines a metric on V. And this metric is called the metric that is induced by the norm. Again, a vector space together with a metric gets a name of its own that is called a metric vector space. So a vector space equipped with a metric is called a metric vector space or metric space. And finally, we can also define a Euclidean metric. We can do this by just using the metric induced by the Euclidean norm. So for r to the n, the metric induced by the Euclidean norm is called Euclidean metric. And it's defined as the distance between x and y, sometimes denoted as d2, to suggest that we're using the Euclidean norm, the 2 norm here, and that is simply the difference for each of the coordinates. So you take x1 minus y1 squared, then you take x2 minus y2 squared, and so on, up to xn minus yn squared, and you take the square root of that whole thing. So that is the definition of the Euclidean metric, and that's the one that we'll most often use. Again, that measures the distance between 2 points as the crow flies. And of course, the other 2 norms that you've seen, the Manhattan norm and the maximum norm, those also induce metrics, and those are known as the Manhattan metric and the maximum metric. Not very surprising. Just one more example, and that is a metric that is not induced by a norm. So there are also metrics that are not induced by norms. A possible example is the discrete metric, and that works on any vector space, because the definition is so general that it doesn't really make use of any specific vector space property. So the discrete metric d is a function from v times v to r, and it's defined by defining the distance between 2 points x and y as 0 if and only if those 2 points coincide, if x equals y, and 1 if they don't. So it's called discrete because it can only take on these 2 discrete values, 0 and 1, and it's 0 exactly if the inputs are both the same, and otherwise it's 1. So basically that metric tells you whether your inputs are equal or not. Okay, and that of course can be used in any vector space, and there is no norm behind that. So you don't have to have a norm to have a metric, but of course if you have a norm, you always also have a metric. So this concludes this first introduction into measuring lengths and distances in vector spaces. In the following chapters, we then extend this to also measuring angles by introducing scalar products. And of course, I hope I'll see you then.